Hello, I'm Jong-In Lee. I'm from Interactive Media Lab at UIST. I'm going to present Reflector, a noble pointing method using on-screen reflection. This work is done with Sunjun Kim, Masaaki Fukumoto, and Byungjoo Lee. Dr. Kim has equally contributed to this research. Reflector is a noble pointing method with hidden design space, the on-screen reflection. On-screen reflection has been considered to be annoying, so some use anti-glare substance to cover it. However, reflection has interesting and unique properties which can be exploited as interaction medium. One of the properties is that frontal reflection of a person's face on a surface is shown straight only to the person itself. There's a person A looking at his reflected face in front, and person B is standing aside watching at the screen. From A's view, he can see his front face straight, but B cannot, because each person sees different reflected image in a different perspective. Second, the ratio of reflected size to screen size is constant regardless of the distance. If you test it with your own mobile phone, if you hold your mobile phone and see your face, the ratio will stay the same in any distance, in close and in far. These unique and interesting property of reflection are not the ones should be removed from the screens, but it has numerous possibilities for designing interaction. To explain this, I'm going to start with the motivation of this work. Then the system overview and implementation of the system will be explained in detail. Last but not least, the user studies for pointing and distance and pin authentication with our method will be described. Screen was an output device that was interactive with traditional indirect input method, such as keyboards or mice. Due to the emergence of touchscreens, screen is not only for displaying visual information, but also treated as interactive medium. Now the screen can be directly interacted not only with touching, but also with mid-air pointing or eye gaze. Numerous interaction methods have been studied regarding this method. However, because of the nature of the relationship between a user and a screen, direct input method have several limitations. The first limitation of the direct input to a screen is that the user's input is exposed. The original function of a screen is to show information to all. If you enter information directly on this output space, then the input will be exposed to everyone. Because of this limitation, personal and private information are also exposed. Therefore, sharing input and output space causes so-called shoulder surfing issues. The second limitation is that direct input method is highly affected by the distance between the user and the screen, because this method requires a user to input directly on the screen with his or her body. For example, touch input is only available in a close distance where a user can reach to a screen. It cannot be used for interacting with screens in far distance. Even when the mid-air pointing method enables the direct input in a distance, the screen is shown smaller as the distance gets further. The possible range for users' movement is reduced as the screen seems smaller, but human has limited movement precision. Eventually, the pointing error highly increases in distance. The same problem occurs for eye gaze method. The possible range decreases in further distance for eye movement. Now I'll introduce Reflector, a new pointing method using the physical property of reflection that solves the limitation of existing direct input method that previously mentioned. Reflector uses the on-screen reflection of user's body to point targets on the screen. We did a market research to see if our method can be applied in a wide range. We gathered the information of 413 screen products from 5 manufacturers. As a result, 53% of the screens were glossy. While glossy screens are widely used because of its advantages, such as more appealing look and better saturation and contrast reproducibility, Therefore, we saw our method can be applied in a wide range. The diagram on the left shows the overview of the reflector system. With the reflector, a user can use its reflected body image as a cursor. The system enables the pointing by estimating the pointing position of reflection. For example, a user can use its reflected right eye as a cursor for pointing on a keypad, as you can see in this video on the right. I'm going to explain how Reflector works step by step. First, front camera captures the user's face. And then with system's reflection model, the captured image is scaled and translated to estimate reflected image, which is shown from the user's viewpoint. The feature points such as eye and nose is extracted from the captured image with the face tracking module in the system. Finally, the extracted feature point, in this case, user's right eye, can be used as a pointing device after the aforementioned estimation process. Please refer to the paper for the detailed explanation of the reflection model for this process. As previously mentioned, the system estimates the reflection by transforming the captured image with the scale and translation factor. For getting these factors, initial calibration is required. A user needs to calibrate by conducting a pointing task with the feature point of his face. In this animation, the user is using his left eye as pointing device. After repeating this about 10 times, the system calculates the scale factor and translation factor based on this user's input. With these factors, the captured image can be transformed to match the user's reflected image. This process took about 1.5 minutes on average and required only once in the beginning. After the initial calibration, the transformation factor should be updated in real time according with the user's varying distance from the screen. The distance from a screen can be obtained with either RGB or depth camera. From RGB image, the distance can be obtained with the relative size of captured face. For example, the eye distance can be used for getting the varying distance. For depth stream, the distance can be directly obtained with the depth value on the face. The scale factor A is updated in real time with this obtained distance value. The system multiplies the initial scale factor A0 with proportion of D to D0, where scale factor A0 and distance D0 are the values from the initial calibration. And D is the distance from the current, D is the distance for the current position. By this process, the captured size is scaled by the updated A value to match the actual reflection from the user's viewpoint in real time. So we conducted 2 user studies to evaluate our system. The first is desktop interface for pointing and distance. In this experiment, participants performed a famous Fitts law experiment, a standard pointing select task following ISO 9241-9. Red and blue target were presented on a black background. Participants were asked to acquire red and blue targets sequentially with each input method. In reflector condition, participant used his or her fingertip for pointing. In eye tracker condition, participant fixated their gaze to point their targets. The targets were selected with dwelling for 0.75 seconds. We used 2 target width and 3 target distance, which results in 6 indices of difficulty. All the combination of target width and distances were randomly presented in a block. For this experiment, 12 participants were recruited from local university. We followed within subject design, which with 2 input distance, 2 input method, and 1 additional measurement on further distance for reflector. All the conditions for each participant were counterbalanced. We set the eye tracker as a baseline input method because the system is available on the market with standardized performance. And each target appeared for only 7 seconds. After this time limit, the trial was treated as a failure. 7 seconds were sufficient time to conduct actual pointing movement with both input methods. And this time limit also prevented the excessive amount of completion time due to the severe errors in the system. As a result, there was no statistical difference of trial completion time for succeeded trials. However, when the failed trials included in the statistics, the trial completion time of Reflector was significantly lower than the one of eye tracker. This is because the pointing position highly jittered with the eye tracker in far distance, which made it impossible to point target in a time limit, so many trials eventually failed with eye tracker. In terms of error rates, there was no statistic difference in near conditions. By the way, Reflector showed significantly lower error rate in far condition compared to eye tracker. As a graph indicates, error rate of eye tracker increased rapidly as the distance from the screen increased. Eye tracker was not even available further from 0.9 meters, but Reflector was available up to 2.5 meters and showed 30% of error rate. I'll explain why Reflector system has lower increase in error rate. As I explained in the beginning, the ratio of reflected face size to the screen size is constant due to the nature of the reflection. Therefore, the amount of movement for pointing is the same in near and far. In other words, the possible input rate does not decrease in further distance reflection. So the pointing error is significantly lower when pointing in the far distance with our method. However, the error rate still increased linearly due to the limited camera resolution. This can be improved by using zooming lens or higher resolution camera for capturing better images in distance. The second prototype was mobile pin authentication system. For evaluation, we implemented a mobile interface that user can point with on-screen reflection for authentication. In this video, the number is entered with Reflector. The pin is 6589. In this experiment, the experimenter entered 4-digit pin with each authentication method. In Reflector condition, experimenter pointed with his reflected right eye and selected by touching any place on the screen. The participants were asked to steal the pin and enter the same as with touch. 10 participants were recruited from local university for this experiment. Authentication method used by the experimenter was the independent variable, and we followed the within subject design. The calibration for the reflector was done only once in the beginning and maintained throughout the experiment. As a result, the participants' hacking success rate of reflector was 20 times lower than the one of touch-based system. Authentication with reflector was much more secure than the one with touch because on-screen reflection shows different image in different position. Therefore, the pointing position is shown in different position that the hacker cannot see the user's input. As you can see in this video, it is not able to see the input from a hacker's view. In summary, Reflector is a novel pointing method using on-screen reflection. It is distant independent with low error rate and also visually private with low hacking success rate. This is it. Thank you for your attention.
Hi, Jun Lee from KAIST, South Korea. Very interesting research on interesting input modality. I have 2 questions. One concerning binocular parallax. Did you encounter any problem with binocular parallax? Because when the user is looking at a screen, but also at a reflection of himself behind the screen, there are 2 distances of interest. So there may be binocular parallax, and I wonder if the users who participated in your user study kind of reported any problem with binocular parallax. And also, my second question concerns dominant eye. So did you always use the right eye, or did you measure the eye-ness of each participant and adjust it as such? Thank you.
Those are all great questions. So the answer for question is that user reported that there is a parallax between the screen and the screen reflection and the content. But as they get adapted to the system, there was no problem for using the reflection for pointing. And the dominant eye is really a good point. I'm glad that you pointed out. So from different eye, you see the different reflected image because the viewpoint changes. So we asked the participant which eye is dominant, so what is their eye-ness? And then we asked the participant to conduct the calibration process with their dominant eye. Yep, thank you.
So about the calibration, is that something you do once when you start the system for the life of the system, or is it something you have to do every day, for example?
You mean the reflection?
The calibration process, yeah.
If you use the same device, only one calibration is required, because if the camera position doesn't change, the calibration doesn't have to be repeated.